Hello everyone. This is the seventh class on the mechanics of solids. In this class, we will study torsional oscillations. What is a torsion pendulum? The figure shows the torsion pendulum. The figure represents a torsion pendulum. Suppose a wire is clamped vertically at one end and other end carries a body. You consider a wire which is clamped vertically at one end. Here it is clamped. Here it is clamped. The wire is clamped here. And the other end of the wire carries a body. You consider a wire which is clamped vertically at one end and the other end of the wire carries a body. It can be disc, bar or a cylinder. In the figure, a disc is shown. That is, our wire is clamped at one end and the other end of the wire carries a disc. The disc has a moment of inertia I about the wire as the axis. This system is called a torsion pendulum. This system is called a torsion pendulum. Now suppose the body, here it is disc, suppose the disc is given a slight rotation in the horizontal plane by applying a couple. Suppose I am rotating the disc in the horizontal plane like this. I am giving a slight rotation to the disc in the horizontal plane like this. Then if the disc is released, what happens? The disc oscillates in the horizontal plane about the wire as the axis. The disc oscillates. The disc oscillates like this in the horizontal plane about the wire as axis. About the wire as axis. These oscillations are called torsional oscillations. The disc oscillates in the horizontal plane about the wire as axis. These oscillations are called torsional oscillation and the system is called torsion pendulum. Let us find out the work done in twisting a wire. What is the work done in twisting a wire? Suppose a wire of length L and radius R fixed at its upper end and twisted through an angle theta by applying a torque at the lower end. You consider a wire which is fixed at its upper end and it is twisted at the bottom end by applying a torque. Suppose the wire is twisted through an angle theta. In the torsion pendulum setup, L is the length of the wire between two portions as shown in the picture. Let R be the radius of the wire. R be the radius of the wire. Now we have seen that when the wire is twisted, then the couple per unit twist of the wire is pi n r raised to 4 by 2L. We have studied this expression in the previous class. That is, the couple per unit twist of the wire is pi n r raised to 4 divided by 2L. What is the torque required to produce a twist theta in the wire? What is the torque required to produce a twist theta in the wire? Let tau be the torque required to produce a twist theta in the wire and this tau is equal to c theta. If c is the couple per unit twist, then if you multiply c with theta, then that will give the torque required to produce a twist theta. Now let us find out the work done in twisting the wire through a very small angle d theta. How much work is required to twist the wire through a small angle d theta? This is given by tau d theta. That is, work done in twisting a wire through a small angle d theta is tau d theta. We have tau is equal to c theta, therefore dw is equal to c theta d theta. That is, the work done in twisting the wire through a very small angle d theta is c theta d theta. And we have to find out what is the total work done in twisting the wire through an angle theta. What is the total work done in twisting the wire through an angle theta? This is obtained by integrating dw. That is, the total work done is equal to integral 0 to theta c theta d theta, and that is equal to w is equal to half c theta square. That is, the work done in twisting the wire through an angle theta is half c theta square, where c is the couple per unit twist of the wire given by pi n r raised to 4 divided by 2L. This work done in twisting the wire is stored up in the wire as the potential energy. This work done in twisting the wire is stored up in the wire as the potential energy. So the potential energy of the twisted wire is half c theta square. Let us find out an expression for periodic time in torsion pendulum. What is the period of oscillation? We know that when the wire is twisted, the potential energy of the wire due to twisting is half c theta square. Also, since there is a disk which is attached to the bottom end, then the kinetic energy of the disk due to rotation, that is equal to half I omega square. This is the wire which is twisted. So the potential energy of the wire is half c theta square, and this is the disk which is rotating or which is oscillating. So the kinetic energy of the disk due to rotation is half I omega square. Now let us find out the total energy of the system. Now let us find out the total energy of the system, which is the sum of the potential energy of the wire due to twisting plus kinetic energy of the body due to rotation. That is, the total energy of the system is kinetic energy plus potential energy. Since the energy is conserved, the total energy of the system is constant. What is the kinetic energy of the body due to rotation? It is half I omega square. Potential energy is half c theta square. Therefore, half I omega square plus half c theta square is equal to constant. Here, omega is the angular velocity. If theta is the angular displacement, then we can write omega is equal to d theta by dt. Now substitute omega is equal to d theta by dt in the previous equation. We have half I, that is half I into d theta by dt whole square, d theta by dt whole square plus half c theta square is equal to constant. Now let us differentiate the above equation with respect to t. If we differentiate the above equation with respect to t, then the RHS becomes 0, because the RHS is a constant and the differential of the constant is 0. Then the LHS is half I 2 into d theta by dt. Then the differential of d theta by dt, that is d square theta by dt square, then plus half into 2 times c theta into d theta by dt, that is equal to 0. Here 2 and 2 cancel in each term. 2 and 2 cancel in each term. So our equation becomes, let us take d theta by dt as a common factor. Therefore, our equation can be written as d theta by dt into I times d theta by dt into I times d square theta by dt square, d square theta by dt square plus c theta is equal to 0. Now, this is possible if either d theta by dt is equal to 0 or I into d square theta by dt square plus c theta is equal to 0. We know that d theta by dt is omega, which is not equal to 0. Therefore, the only possibility is I into d square theta by dt square plus c theta is equal to 0. Let us rearrange the equation, that is d square theta by dt square plus c by I into theta is equal to 0. This is the differential equation of a simple harmonic motion. This d square theta by dt square plus c by I into theta is equal to 0 is a differential equation of simple harmonic motion. Let us compare it with the standard form. Let us compare the above equation with the standard form of simple harmonic motion. D square theta by dt square plus omega square theta is equal to 0. This is a standard form of simple harmonic motion. We have omega is equal to root of c by I. Omega is equal to root of c by I. That is, the angular frequency of oscillation omega is equal to square root of c by I. Now, what is the time period? T is equal to 2 pi by omega. T is equal to 2 pi by omega. Therefore, T is equal to 2 pi into root of I by C. T is equal to 2 pi into root of I by C. This is the expression for time period of oscillation. T is equal to 2 pi into square root of I by C. In this section, we will see how torsion pendulum can be used to determine the rigidity modulus N of the material of the wire. We know that the period of oscillation of a torsion pendulum T is equal to 2 pi into square root of I by C, where I is the moment of inertia of the disc about the suspension wire as the axis. The disc is oscillating about the suspension wire. I is the moment of inertia of the disc. Here I is given by mr square by 2. M is the mass of the disc and r is the radius of the disc. So by measuring the radius and mass, we can calculate the moment of inertia of the disc. Then what is C? C is the couple per unit twist of the wire, and we have seen that it is equal to pi n r raised to 4 divided by 2L, where n is the rigidity modulus of the material of the wire, L is the length of the wire, and r is the radius of the wire. We have to find out the rigidity modulus n from these equations. First, let us write the expression for T. T is equal to 2 pi into root of I by C squaring. T square is equal to 4 pi square I by C. 4 pi square I by C. Let it be equation number 1. we have the couple per unit twist C is equal to pi n r raised to 4 divided by 2L. C is equal to pi n r raised to 4 divided by 2L. Let this be equation 2. Now substitute 2 in 1. Substitute 2 in 1. Substituting equation 2 in equation 1, we have t square is equal to 4 pi square I divided by pi n r raised to 4 into 2L. That is t square is equal to 8 pi square IL, 8 pi square IL divided by pi n r raised to 4 divided by pi n r raised to 4. Pi and pi cancel. So t square becomes 8 pi IL divided by n r raised to 4. That is t square is equal to 8 pi IL divided by n r raised to 4. Where n is the rigidity modulus of the material of the wire, we have to find out an expression for n. Therefore, n is equal to 8 pi I divided by r raised to 4 into L by t square. L by t square. This is the equation to determine the rigidity modulus n of the material of a wire. This is the experimental procedure to determine the rigidity modulus of the material of a wire. A heavy disc is suspended at the end of the experimental wire, which is fixed at the top. This is the heavy disc which is suspended at the end of the wire, and the wire is fixed at the top. We have to find out the rigidity modulus of this wire. The disc is carefully rotated in a horizontal plane and released. The disc is carefully rotated in a horizontal plane and released. Then what happens? The torsion pendulum makes torsional oscillations like this. The torsion pendulum makes torsional oscillations like this. Now the time for a definite number of oscillations is noted. In the tabular column, the time for 10 oscillations are represented. The time for 10 oscillations are noted. To minimize the error, the experiment is done 2 times and the mean time t for 10 oscillations are tabulated. From this small t, the period of oscillation, that is time for one oscillation, is calculated. Just divide small t by 10, you will get the time period capital T. Now measure the length of the wire. Measure the length of the wire small l. Measure the length of the wire small l. Then L by T square can be calculated. Because we know the period T and length of the wire, therefore L by T square can be calculated. Now the experiment is repeated for different length of the wire. Now change the length of the wire. Change the length of the wire. Do the same experiment. Find the time for 10 oscillation. Then find the period capital T. Then again for this new length, find out L by T square. Then again repeat the experiment by varying the length, and L by T square is determined. Now take the mean value of L by T square. Take the mean value of L by T square. Now using a screw gauge, the radius of the wire R is measured. Using a screw gauge, we can measure the radius r of the wire. Then measure the mass of the disc. The mass of the disc which is suspended at the bottom end of the wire, and measure the radius of the disc. Radius of the disc is capital R, mass of the disc is capital M. Then the moment of inertia of the disc is given by mr square by 2. We can calculate I is equal to mr square by 2. From these readings, we can find out the rigidity modulus N of the material of the wire as N is equal to 8 pi I by R raised to 4 L by T square. 8 pi I by R raised to 4 L by T square.